Okay, welcome. The topic we'll be discussing in this session is monitors. So in the last session, we have discussed about semaphores, but there are certain problems with semaphores, and that is the reason we are introducing the new concept called monitors. Basically, the working mechanism of monitor is similar to semaphore. It is not much different, but only thing is the monitors provide a defined structure so that whatever the mishap that may happen in semaphores, that will not take place in monitors. Okay, actually semaphores provide a convenient mechanism for process synchronization. But what happens in the sense, if semaphores are used incorrectly by the programmers, if semaphores are used incorrectly by the programmers, then it may create some issues. Okay, so what are those issues that may be created by the by the semaphores if the programmers use it incorrectly? That we will discuss. So at the core, the problem with the semaphore is it leaves everything to the programmer. The programmer should very carefully program in such a way that the semaphore is not creating any issues. Okay, so for each and every process, the programmer should follow certain formalities. If the formalities were not followed, then semaphores may create problem. Okay, right? So basically, semaphore it uses two signals: wait and two operations: wait and signal. Okay, so before acquiring the lock, it should call wait. Similarly, after acquiring the lock, it will enter into the critical section, and before coming out of a critical section, it should call signal. So this wait and signal should be correctly used by the programmers. It should be correctly used by the programmers. If it is not correctly used, then it may create some issues. Okay, so what are those issues that we will discuss, and how monitors is going to rectify that? Okay. See, the way in which semaphores and monitors they work, both are same. Okay, the only difference is semaphores leaves everything to the hand of the programmer. That is, a programmer is fully responsible to ensure that semaphores is working properly. But sometimes programmers, maybe intentionally or unintentionally, some errors may happen which may lead to incorrect behavior of the semaphores. But such issues will not happen in monitors, because monitors provide some predefined structures where programmer cannot do any mistakes either knowingly or unknowingly. Okay, so that is how monitors differs from semaphores. Otherwise the operations they perform are actually same. So first let us understand under which circumstances semaphores will create problem. So this is the general protocol the semaphore should follow. uh, the general protocol the semaphore should follow is wait and then critical section and then signal. Okay, so the general protocol the semaphore should follow is, first it should call wait. First it should call wait as long as the lock is not available. So wait on mutex or lock, whatever it may be. Mutex is also a lock, one type of lock. Okay, so wait on a lock. As long as the lock is not available, it will be keep waiting. As long as the lock is not available, it will be keep waiting. If lock is available, then it will enter into the critical section. Once its job is in the critical section is completed, then it should call signal. So this is the actual flow of a semaphore if it is programmed correctly. Okay, but say if it is programmed wrongly, if it was programmed in the reverse way, instead of calling wait, so it can be either lock or mutex. Okay, so say that instead of calling wait first, so here also it is either lock or mutex. Okay, so instead of calling wait first, say we have called signal first. Okay, after calling signal, the process is entering into the critical section. Now this is one such issue, one such case where programmer can make a mistake. So instead of following the pattern wait of mutex and then critical section and then signal of mutex, if the programmer did it in the reverse way, first if he called signal and then critical section and then wait of mutex, then this will this will eventually lead to a circumstance where more than one process will be allowed to critical section. If this type of construct is followed, then what will happen in the sense more than one process will be entering the critical section. Okay. Okay. So more than one process will be entering in the critical section. Okay. So which is not at all allowed. So it means the basic solution for the critical section problem, mutual exclusion, is defeated. Okay. So if the programmer use it in the reverse way, this is the problem it will create. Similarly, say you should call wait of mutex first and then critical section and then signal of mutex. Say at the end also the programmer is calling wait of mutex. He is not calling signal of mutex. So in that case, what happens if process pi at first it calls wait of mutex. So it waits as long as it gets the lock. After acquiring the lock, it performs the critical section activity. Then actually it should release the lock by calling signal. But now once again it is calling wait. But now once again it is calling wait. So what happens in the sense this critical section will be always occupied by the process pi. This critical section will be always occupied by the process pi and no other process will be allowed to enter. If other processes are waiting in a queue, say pi plus 1, pi plus 2, all those processes are waiting here, they will not be allowed to enter and they will be keep on waiting, resulting in a deadlock. Okay, so this condition may result in a deadlock. Okay, so if instead of calling wait critical section and signal, if you call wait critical section and wait, then this is the problem that will be created. If the programmer has either omitted wait or signal or both, say the programmer has omitted wait, initially he should write wait at first. If he has omitted wait, then what will happen? More than one process will enter the critical section, which will result in defeating of mutual exclusion principle. If he forgot to call signal, if he has not called signal, then what will happen? It will result in what you call deadlock. Okay. So these cases, under these circumstances, semaphores will create problems. Okay. Because it depends on the programmer. It leaves everything to the programmer and it expects the programmer to ensure that they are using the instructions wait and signal appropriately. But if the programmer fail to do so, then it may create these kind of errors. Okay, so basically the errors created by the semaphores or may lead to deadlock and starvation. Okay, actually if semaphores are used correctly, then it will not lead to these errors, but we cannot always guarantee because everything is in the hands of the programmer. The programmer should ensure he is using correctly. Okay, but sometimes if it is not done that way, then it may lead to these issues. Okay, so to address these issues, there is another concept introduced and that is called as monitors. So what monitors does in the sense, it does not leave everything on the hands of the programmer. Rather, it provides a high level abstraction for process synchronization. So high level abstraction means what? High level abstraction means something like a class. You know what is a class? A class is a blueprint of the real world entity. So it provides a high level abstraction or an abstract data type. Okay, it already defines the monitor something like a predefined class. Okay, like how in Java there are predefined classes. So like that, monitors will be defined as some predefined class. Class is nothing but an high level abstraction or an abstract data type, and the programmer can use that and the programmer can use that and monitors will ensure that only one process will be active inside the monitor at a time. Only one process will be active inside the monitor at a time. there cannot be any time where there are more than one process. Okay, so more than one process can be there in semaphores if the programmer used the constructs wrongly. If the programmer uses the wait and signal constructs wrongly, then it may so happen that more than one process may enter the critical section. But in monitors, that cannot happen. Even if programmer makes a mistake, first of all, programmer cannot make a mistake because everything is not given to the hands of the programmer. The set of tasks that the programmers can do is very limited. So monitors ensures that no such errors will occur. So this is the general structure of a monitor. So in a given programming language, it is considered that the monitor will be predefined as a class. Okay. So monitor, this is a some monitor data type. Okay, there is already you have a predefined class monitor. For that monitor, you are creating a monitor name. Okay, so this okay, this is so for that monitor you are creating a monitor name, some variable name, like how you are writing class name. Similarly, this is monitor name. And then here comes the shared variables. Whatever the shared variables that will be used by the process that want to use this monitor, all those will be declared here. And what are the procedures connected with this monitor, all those procedures will be coming here. And what is the initialization code. So this is how the monitor is defined. Okay, but only this much is not enough. This is not that powerful. So something beyond this the programmer should do, that is he should create some conditional variable. He should create some conditional variable. So I'll explain this diagram later. He should declare some conditional variable. So this here two conditional variables are declared, x and y. So basically these conditional variables are nothing but the shared variables which are inside the monitor. So this diagram is nothing but this is the logical or schematic view of the monitor. So in the previous case here you have seen this code for monitor. So the code for monitor contains what? It contains shared variables, procedures, and initialization code. The same thing is in this diagram. So this oval thing you can consider it as a monitor, and it contains what? It contains shared data. It contains some set of operations which is called as procedures. Okay, like how in Java a class contains variables. So this is shared data, that is variables, and these are the, like Java inside a class you will have methods. Okay, so these methods here it is called as operations or procedures, and then there will be some initialization code. Okay, so this condition data, what is condition data? Condition data are shared variables. So this x and y are condition data. Basically these are the shared variables which are available here. Okay, those variables we are creating using this keyword condition. Okay, now on this condition variable the programmer can perform only two operations. One is wait, the other one is signal. Okay, one is wait and other one is signal. So if the programmer calls wait, if the programmer calls wait, then what will happen in the sense, this this particular the the monitor for this particular, the monitor which is using this particular shared variable x, sorry, the process which is using this shared variable x. Okay, if a process calls x dot wait, say the process pi calls x dot wait, then the process, then it means pi is using the shared variable x. Okay, so pi will be suspended until some other process calls x dot signal, until some other process calls x dot signal. Okay, until then it will be suspended. Okay, so why it calls wait in the sense, I'll come to that later. Okay, but just now understand that if a process pi calls wait over a shared variable x, then the process pi will be suspended until some other process calls signal on the shared variable x. Okay, so when some other process calls signal on this shared variable x, then whichever the process waiting for that will wake up again and it will come. Okay, similarly Similarly, signal, what it does. So signal, if somebody calls signal on X, then this will resume one of the process that invoked previously wait. Okay. So if PI is invoking wait on X, then PI will be suspended. Okay. And if PJ after some times, say after uh, 50 milliseconds or 100 milliseconds, then PJ calls signal on X, then PI will be invoked again. Okay. So what is this suspending? Okay, so for that, see, basically monitor maintains two queues. Basically monitor maintains two queues. One is called as entry queue. One is called as entry queue, and the other queue is on for every shared variable. It will maintain a queue. For every shared variable, it will maintain a queue. Okay, so initially, if nobody is using the monitor, if nobody is using the monitor, then the monitor will just enter. Okay. If nobody is using the monitor, and if a process PI want to use the monitor, it will just enter, because there is nobody is using the monitor, so it can use the monitor. Only one process can use the monitor at a time. So let us assume PI is using the monitor. Now say if some other process PJ comes, then it will wait in the entry queue. Second number it is waiting. Say another process PK comes, so that will also wait. Another process PL comes, that will also wait. Another process PM comes, that will also wait. So all these processes will be keep waiting. Okay. So this is what the entry queue for. The entry queue, only one process can be inside the monitor at a time. So if process PI is using one of these procedure, process PI will be using only one procedure. It will not use all the procedures, but still only one process can be inside the monitor to ensure that the critical section problem does not occur. Okay. Now if PI comes out, then PJ can enter. Okay, it's like that. But sometimes what happens in the sense, PI might not have completed. PI might not have completed, but it may want to suspend itself. Suspend means it may want to wait for something else to happen. So then in that case, it is not going to do anything. In that case, the process PI is not going to do anything. So process PI can be removed from the, what you call, from the monitor, so that some other process can enter. So that some other process can enter. Okay, for that it maintains another queue. For that it maintains another queue. So the concept here is PI is executing, still its execution is not finished, but in between it want to break, it want to give a halt for some time, maybe if some IO operation or whatever it may be, it want to halt, and then it may want to resume after a period of time. So during this halting period, you need not keep PI inside the monitor, because if the operating system keeps PI inside the monitor during this time, then all other process also will be blocked unnecessarily. So during this time, PI should be removed out of the monitor so that other process can enter. Okay. For that, another queue is maintained, and that queue is on the condition variables. Okay. So if PI, let us assume PI is using the variable, PI is using the shared variable X. PI is using the shared variable X, and PI is executing, and in between it want to wait for sometimes. It want to wait for some time. Okay. Then what it will do, it will call X dot wait. Then process PI, what it will do, it will call X dot wait. That is on the shared variable, it is calling the wait. So what will happen, the process PI will be moved to the suspended queue. So this is suspended queue. So here process PI will come here. So it is waiting on the variable X. That is something to happen for X, until that it is waiting. Okay. So now it is no more inside the monitor. It is just waiting in this particular queue. Now some other process, say already PJ is waiting in the queue. So let us assume PJ is waiting here. If some other process PJ is waiting here, now this process will enter, and it can use the monitor now. Okay. So now PJ is also completed. Now, next another process PK comes. PK is performing the task. Okay, but in between, say PK while completing the task, after completing its task, it calls it calls x dot signal. It calls x dot signal. Okay, so if it calls x dot signal, then if there is any process waiting for x for some operation to happen, that process will be once again invoked. Okay, so before leaving, PK calls x dot signal. So already PI is waiting for that. Okay, so now PK calls x dot signal and it will go out, then PI will enter once again. Okay, so this is why the wait and the signal concept is used. So basically monitor uses two types of queues. One is the entry queue and another one is the queue associated with the condition variables. Okay, and the working of monitor is similar to that of the semaphores. It also uses the wait and signal constructs, but the only difference here is that it ensures that the no times two process will be allowed to enter the critical section at any point of time. So it is not left to the hands of the programmer. Rather, the monitor constructs itself ensures that such thing does not happen. Okay, so that's it about monitors. Let us stop here. Thank you.